Hello everyone. In this lecture, we'll be going over the alignment algorithms like direct preference optimization, simple preference optimization, odds ratio preference optimization, anchor preference optimization, and Kahneman-Tversky optimization. And we'll be going into like why we needed all of these algorithms, and we'll dig deeper into each one of them. So before jumping into the alignment algorithms, let's first try to understand what are log props. So let's say you have a bunch of transformer layers and you start a autoregressive transformer from the beginning of sentence token. Then it goes through a lot of transformer layers and you get a logits, which is dimension of vocab size. And after that, if you take a softmax followed by log, you need to do that because you need to find the probabilities of uh, each of the elements in your vocabulary. And the high, if you are doing greedy decoding, then you just pick the highest probable one. But the point being that you need to take softmax to convert the logits, and these logits can like range from these are basically real numbers, so they can be negative, but probabilities have to be positive. So you have to take a softmax and followed by logarithm. And after doing log, you know that the first word is hello, so you will pick out the log softmax of the token indices hello from your vocab size. It can be here, here, anywhere, and you just pick that one out and you have got a value here. So this is basically the log prob of the first token in your in your sequence. Now, if we go to the next token where you have beginning of sentence and you have already decoded hello, then you again pass through the transformer layer. You produce the logits followed by log softmax, and now you just pluck out the value which is at the index for word in your tokenizer, and you get back the value, the log proc value for word. So you have basically got like from the previous slide, the value of log prob is 1 minus 1.3, and the next slide you have got a value of minus 1.5, and these values are negative because you are taking log of a probability, and probability is between 0 to 1. When you take log of a value which is between 0 to 1, you get a negative value. So that's why this log prob is basically a negative value. And now for the entire sequence of hello world, you got minus 1.3 for hello, and world given hello, you got minus 1.5. So the total log prob, the sum is minus 2.8. So this is the summation of your log prob for the entire sequence. And now drawing some parallel to reinforcement learning. In reinforcement learning, you generally have an action at each state. But when you translate reinforcement learning to language model, your entire output is an action. Hence, you need to um, add up all the log props and into one value to give what's the action for the reinforcement learning algorithm. So as we treat the entire output to a action, so we need some way to aggregate all these log props, and we do that by summation. So if you increase the probability of each of this token, so that means you are increasing the log probs, and if this is a loss, then you are basically reducing the loss. That's what we want, to reduce the loss and increase the probability of these relevant tokens. So this is the basic idea about log probs, and we'll be using that all throughout our alignment algorithms. So as I said, the RL objective is basically for language model. You have a policy. A policy means at each and every um, generation, like you are generating the next token, what's the probability of all your possible words? So you keep on doing that for the entire sentence, and those probabilities at each time step is basically the policy of your model. And our aim is to minimize this sum of these log props so that you can maximize the next token probabilities. Uh, so the reward in RL for LLMs is basically are is going to come from this log props, where you are trying to maximize the next tokens that you got in your output sequence. But but you need a way to have an anchor point so that you do not introduce instability in your training. So the most important part in training is that your training runs are stable, the loss curve is stable, and people have found that if you anchor your currently running policy with the reference policy is what, like, let's say you do pre-training and then you do supervised fine tuning, uh, and you have a model which can follow instructions, and that can serve as a reference policy to your RL model. And that RL model, uh, uh, to train that RL model, you should not deviate too much away from your reference policy. So that's why we to maximize the reward under this constraint that it should be close to the reference policy or the policy that you started during your checkpoint. So this also reduces reward hacking. So if you just like blindly have this R of x comma y, so your model will just try to amplify this reward, so you might just get hack the reward, and you might not have some anchor point to the reference policy. So this scale divergence is also kind of important because you need to maximize reward given that you have this KL constraint. So so our RL objective is pretty simple. Like you want to maximize the reward of your generations, stay close to the reference policy, and as I defined log probes, so log probes can serve as a proxy for the reward. So let's start deriving our direct preference optimization objective function. So as I said, this is our RL objective in deriving in aligning our models, where you have a reward function and then you want to stay as close as possible to your reference policy, and you have this scale divergence. So you want to maximize your reward given this constraint. And most of the libraries like PyTorch and everything, they try to minimize something. So it's just better to express it as a loss function and try to minimize it. So, and you can do that by just taking by negating this whole thing. So if you negate the whole thing, then this term will come forward and r comma x comma y will come back. So this 1 by beta term is it's kind of a constant, so it doesn't matter. So just for cleaner arithmetic, the authors shifted to 1 minus beta point and didn't choose to keep the beta here, but it kind of doesn't matter because it's a positive constant. Now let's imagine, like, hypothetically, uh, we need to have approximate this policy. We want to learn this, and we are given a checkpoint of the reference policy, and we want to maximize the reward here. So let's say you are given a Oracle policy, and the role of the Oracle policy is to maximize starting from this reference policy. It wants to maximize the reward. So you want to maximize the reward given the reference policy, and let's say you can generate infinite things from your model, and given this infinite things, and you can generate all set of possible completions for a prompt. And if you take the summation and you have this as your numerator, so it means that you have kind of approximated the Oracle policy, and you just pick and you just maximize this. You just pick the policy which gave you the maximum reward. So it means you just take a prompt, generate all possible kind of outcomes, and you just pick the policy that gave you maximum reward. So we call this denominator as partition function. So I'll just substitute this function with z of x. So now your oracle policy becomes pi star of y. Y is your completion and x is your input. uh, Y given x, and this is your reference policy, and this is a reward, and this is a partition function. So now we need to find this oracle policy. So before going into the oracle policy, let's first see the objective that we had earlier when we took negative of our RL objective, and we saw that. So if you connect back here, we wanted to maximize, and then we took a negative and we found this. So I'm starting from here again. So I'm starting from here. So we can substitute from our oracle policy, we can substitute this pi ref here. So we can take z of x here and exponent on the denominator, and we can take this pi ref, whatever we had on this LHS, we can just like substitute it back here. So substituting pi ref, we got this value, this log of pi y given x, and this is the oracle policy, and this zx came from, is a partition function, and this is a reward, and this is 1 beta r x comma y. This is the reward that you earlier saw in the RL objective. So now you can use property of log. So let's keep log pi y given x and pi star y given x together, and this is in denominator. So if you log a by b is equal to log a minus log b, so this one comes to here, and now and log a into b equal to log a plus log b. So, and when you take a log of an exponent, you just get back this value. So you will get back this value, 1 beta r x comma y, and now this kind of cancels out. So you have cancelled out the reward that you are trying to objective. So this is just an arithmetic trick here. So now your oracle policy, your partition function, and your policy that you are training, so you have kind of expressed your policy as in form of your oracle policy and the partition function. And now this comes back to that we cannot generate all possible completions from the model. We cannot compute this z of x, like as I have told you here. So it means that taking your pi ref policy and generating all possible completions for your model, which is simply not possible. It will take like millions of billions like computational runs. So we need a way to uh, uh, cancel out this, and also look what we can do about this oracle policy, because we don't have these two things now. We just have our model. And now coming back to how we expressed our oracle policy. In this oracle policy is basically the pi star x. This is same as what I expressed here. So this is how I expressed my oracle policy, though this is the same thing that I'm repeating again. So you have pi star x, you have pi ref, and you're generating all in the denominator, you're generating all possible responses from pi ref x, and this is your reward. So this is the oracle policy. So now let's take log on both sides. So you have on LHS log pi star x, and this is your reference policy. And if you take log here, so this is log of pi ref x minus log of zx plus a log of an exponent is basically you will get back this value. So this will be plus here. So you get back this plus 1 by beta r x comma y minus log of zx. So you got this after taking log of the oracle policy. So now you can take the reward that you have here, this reward, to one side, and take all of the other things to other side. So your reward can be expressed at this formula, and you can just like take reward on the LHS and take everything on the RHS, and you'll get back this. So this is kind of profound. So suppose imagine, if you know about PPO or RLHF, so the authors had to train a separate reward model to reward the trajectories, and the reward is kind of like really difficult. Like you have to take care of reward hacking. You have to see like um, you are properly training or covering all the edge cases. But here you just got the reward as a function of your Oracle policy that you are trying to find. So your if you look at the paper DPO, their heading is your language model is secretly a reward model. So if you can express the reward model as form of your policy, so it means that the reward can be approximated with your policy. So your policy is basically a reward model. So in a RL objective, the reward that I was saying is basically can come back from the policy, and the policy is the log props that I mentioned earlier. So so as you have got the reward now, but now how to express this reward? So there comes another theory called as Bradley-Terry model. So Bradley-Terry model was basically designed to uh, approximate the reward between some winning stuff and some losing stuff. So uh, it shows a probability of a event happening will be which will give you net positive outcome, then an event happening that will give you negative outcome, given the inputs, is expressed by this formula. So this is simply the Bradley-Terry model, and we can use this to approximate the reward in our DPO objective. So now let's go back to this Bradley-Terry model, and we have this Bradley-Terry model that I showed you earlier, and just remember that this is the reward that we mentioned here, like where we did some arithmetic to take the Rx comma Y to LHS and all of these things to RHS. So this is your reward. So you can substitute the reward in Bradley-Terry model. So if I just substitute it, this is your Oracle policy and this is your winning outcome given the prompt, and this is your reference outcome. So you just get back the Bradley-Terry model expressed in our reward. So this takes some time to look at this, and so you're just like basically substituting the reward here um, in your Bradley-Terry model. So now to do some arithmetics, you can take the numerator here, take the whole thing and divide, take it to denominator. So basically take the numerator and divide in both numerator and denominator. So if I divide the same thing in numerator, it will be 1. As you can see here, it's 1. And all the rest of the stuff, it comes back here. So you can see here you have expressed it, and the losing response and the winning response are together now. And now applying the trick of exponent A by exponent B is equal to exponent A minus B. So you can just take this exponent, and so basically everything here minus everything here. When you do that, now you have basically cancelled z of x. So the thing that we started out as to be intractable, like we cannot generate every possible response from the model, is basically cancelled out. So this kind of means that you cannot approximate the partition function, you cannot generate every possible outcome from the model. But if you take a winning response and a losing response and you take the difference between them, so you will basically cancel out the partition function and you don't have to approximate that. So the reward that you are going to learn from your winning and losing response difference is going to satiate into as if you approximated the whole possible outcomes and then you approximated the policy. So this is like a cool trick that to cancel out log z of x. So now we get back this value after cancelling the partition function b pi star ylx and b pi star ywx. So now let's also simplify this a bit more. So this is our sigmoid function, which is expressed as 1 minus 1 plus e to the power minus z, and this part is your entire z, right? So this part is your z, and if you just take the minus of it, you get to your DPO loss function. So this whole thing is your DPO loss function, and it comes from when you expressed it as a sigmoid, and you can see here the sigmoid value, which is expressing whole this thing. And then we take a log, so that, and because in log space, the good thing is like the values do not shoot up too much. So that's why it's a good training stability trick to apply log to your values so that they are more contained. So this is the objective of DPO that we derived. Please go back, feel free to go back and revise what we did and try to make sense of the arithmetic. And but yeah, like the main thing is like we arrived at the DPO objective where you see the winning response, and you are trying to also stay close to the reference policy, like what we discussed, so that we don't reward hack. And also like you have the losing response and you are trying to go to this uh, uh, reference policy too. So this is your objective for DPO that we derived. So how did this help? Before, like when you are training for PPO or RLHF, you need to train a reward model, and it was kind of painful because the reward model is also a language model. So let's say GPT-3, which was like 175 billion parameter. So the reward model would also be same parameter count. So you are like now managing 350 billion parameter model. So this kind of increases the memory footprint of your model. Now we don't need a reward model because you can approximate the reward with your policy. So that's a great thing, and this is how DPO simplifies the PPO RLHF by taking the reward and expressing as policy. So hence, your language model is secretly a reward model too. So, but DPO has some issues, and some subsequent papers that came after DPO tried to address this issue. And these are the three issues, but we'll be diving deep into each one of them. Uh, First is log probes, nomination, and reward. So let's go to that issue of reward hacking. Suppose let's imagine that you have two preferences. One is the winning response and the losing response, and your length of the winning response is it's very long, and your losing response is super short. So now you are taking the log probes of the winning and the losing, and also minded that the log probes are negative values because if you remember here, if I'll go back, uh, so the log probes that you got are like negative values. So imagine like summing a ton of this. If your winning response is huge, so you are like, this value would be super negative. So I'll go back. Yeah, so you sum the log props of the winning, and you have the log props of the losing, and you see that the log props is it's like it's like more negative. I just kept it minus minus because it is very negative as compared to losing. So as your log props of the winning response is very negative, and to to decrease the loss, the model has to artificially inflate the probabilities of the winning response of all the tokens in your winning response. So this is the log graph. If you see, like, so what the model will try to do, it needs to reduce the loss. Hence it needs to take the log probes as close to zero. It needs to take the loss as close to zero, and the best way to do is uh, to take the probabilities, because log probs is basically log of the probabilities, to take the probabilities as close to 1. So if you can take that, then you can reduce the loss by a lot. So this is reward hacking. You are just like, if you have like a lot of big responses or like longer responses for winning, so you just like artificially inflate the probabilities of the winning response, and this can lead to reward hacking. And also sometimes the chatbot is very verbose, so it kind of like learned that if I increase my response, then um, and my loss could go down. So uh, uh, this is one of the problem with the DPO, and the solution that is pretty simple. You just divide it by the length of the response, so that now it is like normalized. Even if you have a long sum of the log props, if you are dividing, then it gets normalized. So yeah, the solution to reward hacking is much simpler. Just divide by the length. And another thing is like, you have lot of memory constraints. Like if you see GPUs, they, if you take the GPU like H100, they have only 80 gigs of VRAM, and you can fit only like smaller models. And now you have to also fit a reference model, and you always have to pay a forward pass for every batch. So that's kind of a lot of computational power. So can we get rid of the reference model? And also another thing is training inference mismatch. So while training, you have the reference model. Like if you see the DPO loss, you have the reference model while training. But after training, you do not have the reference model. So you have basically your reference model is useless after training. So, and also during inference, you do not use the reference model. So there is kind of a training inference mismatch. So uh, there isn't much point in having the reference model during training if you are not going to use during inference. And also like the reference model that is generally trained may not be super aligned, or may not be the best place to may not be the best anchor, uh, in better words, may not be the best anchor to always aim to. So it's fine to ignore the reward model. It will save you memory, and also like you won't have this training inference mismatch or a bad anchor. If your reference policy is bad, then you'll just like get stuck with what you have. So SIMPO loss, or simple preference optimization loss, simplifies it by just uh, dividing by the winning response and losing response, so that you normalize the length of the log props. And it doesn't have a reference model. So here if you see, there is a reference policy, but it doesn't have any reference policy. Okay, now let's start talking about another form of direct preference optimization, which is called as anchored preference optimization. And people are at least I know Hugging Face has shifted to APO instead of direct preference optimization. So let's see some of the issues with the DPO. So if you see, this is the objective of DPO. So here, like DPO objective only cares about this difference in the winning and the losing response. So it can either increase the likelihood of the winning response and increase the likelihood of the losing response, but by less. So you still have a difference here, or it can um, reduce the likelihood of losing response by a lot and reduce the likelihood of winning response by little, and you still have some difference here. So DPO objective can function either ways, which is problematic, because we if you want very finer control, like you want the model to learn everything about the winning response, you cannot control that with DPO, because DPO object, so this dynamics can just like change from prompt to prompt, and you don't have any explicit control over this. So as I said here, so suppose you are adapting a stronger model with preferences generated from a weaker model, or you are aligning a weaker model with preferences generated from a stronger model, you have two different kind of alignments. but DPO can just like align them in arbitrary order. So you don't have any control. So suppose you have a stronger model and you have preferences from a weaker model, you would like to optimize for the difference in the likelihood for a winning response and a losing response. And you just like to optimize for that. You just don't want your stronger model to mimic the weaker model. But if you are having a weaker model, first objective is for it to imitate the stronger model, winning responses. And the second objective is to maximize the difference between the likelihood of winning and losing. So the relative increase or decreasing log likelihood kind of matters here. You have like different objective here, and you need finer control, and APO kind of provides you that. So so suppose you have a stronger model and you are aligning them on weaker model preferences, then you need to optimize for the difference in the log likelihood. You need to reduce the likelihood of winning response and reduce the likelihood of losing response even more. Uh, as you don't want the stronger model to mimic the weaker model, so you cannot like simply increase the likelihood of the winning response. So it means that your stronger model will start to imitate the weaker model, and that's bad news. You don't want to do that. But you want to reduce the likelihood of this losing response by a lot so that your stronger model is aligned. So you want the winning response to have lower likelihood and the losing response to have even lower likelihood. So this is the case one. So let's see how APO balances this out. So the loss function that APO provides is APO down, where if you see, so in machine learning we try to reduce the loss. So if you are reducing the loss, so it means you want to reduce this one. So as I said, you want to decrease the likelihood of the winning response from your stronger model. You don't want your stronger model to produce outputs from the weaker model, even if it's winning. You want to decrease by some amount, and and you also want to amplify the difference between the winning and the losing. So you want to increase this difference. So which means the losing response likelihood should be really really low, which is shown here. So APO down is kind of very helpful if you are aligning a stronger model with a weaker model preferences, and you don't want the stronger model to imitate the weaker model. So APO down is helpful. So now let's look at the second case. In the second case, if you are adapting a weaker model to a stronger model, then you need to increase the likelihood of winning and decrease the likelihood of losing explicitly. So you need to increase the likelihood of winning and decrease the likelihood of losing. So if you want to have this explicit control, APO also provides another variant, which is called as APO 0. Here, the winning one, so you want to minimize the loss, which means you want to maximize this because there is a negative term here. So you want to maximize this, which means you want to maximize the likelihood of the winning response. And you want to minimize the loss, hence you want to minimize this, which means minimizing the likelihood of the losing response. So APO 0 and down has two different kind of applications, and based on what model you have and how you want to align, you can pick one of those things. And another interesting thing from the paper was that your alignment direction from your winning and losing response needs to be few and irrelevant dimensions. And in that case, learning signal would be cleaner. So suppose like you have a losing response which is helpful, but a winning response is little bit more helpful. So the learning signal is kind of difficult to grasp because it is little bit helpful, but it might be helpful for someone, but it might not be helpful for another person. So the learning signal isn't very clear. So first thing is like we want the winning response to have uh, like minor cosmetics on the losing response, and you are not aligning on many dimensions of preferences. You are aligning on few dimensions, like you're just aligning on harmfulness, or you're just aligning on helpfulness, or just aligning on spelling mistakes. So what they do, they generate the losing response with a very weaker model, and then they just take GPT-4o and say it to modify the losing response and into this winning response. So you can see like this, it's a very in place cosmetic modifications, and this can like really help for the model to have few irrelevant dimensions. So this is all about uh, anchored, anchored preference optimization. Now let's move on to the next one. um, it's called as odds ratio preference optimization. And before jumping into ORPO, or odds ratio preference optimization, let's try to think about something when you're doing DPO. Suppose you have a prompt. Please respond the answer by starting with let's think step by step. And your winning response starts by let's think step by step, dot dot dot, it completes the response. And your losing response is also let's think step by step, dot dot dot, let's say. But when you take this subtraction between your winning response and losing response, or as all these tokens are identical, or the initial tokens are like really identical, you are just having no learning signal from identical tokens at the start of your sentence. If they are like um, so if they are same, so your gradients kind of cancels out. So your model doesn't know that it has to produce this let's think step by step. And but in the prompt you explicitly asked to produce this let's think step by step. But if you take the difference, you're kind of ignoring that learning signal, which is problematic. So to solve this issue, generally people do SFT so that the model learns, okay, I need to start with let's think step by step. I need to reduce that cross entropy loss. And then while aligning, you can just align by winning and losing response. So first we need to do SFT, then followed by DPO. Else DPO is going to only miss the initial substring match between the winning ratio and losing response. So that is kind of problematic, and we need to solve that issue. And the way to solve it is by having both SFT and alignment together as a optimization, so that you don't have to do SFT as a like different pipeline to DPO. So let's uh, jump to odds ratio and how it is helping with that. So odds ratio, if you know about probability theory, odds basically means a chance of event happening to the chance of event not happening. So probability of an event is 0.8, then the odds is 0.8 by 1 minus 0.8, which is 4 is to 1. So there is a 4 is to 1 chances of this event happening, and this is the odds formula. So the ORPO loss is basically taking the odds of the winning response and the odds of the losing response, and it is converting it into a logistic regression problem where um, this sigma of log of this odds and odds ratio, where it is trying to increase the probability of the winning as compared to the probability of losing. So if you increase these odds of the winning response as compared to losing response, so you're basically getting the ORPO loss. And this log is basically taken for instability, and this sigma comes from like clipping the values from in the sigmoid range. So now you have basically converted the DPO loss into odds ratio loss, where you are optimizing to have more probability for having this winning response as compared to this losing response. And you have converted into a logistic regression problem, that you want to increase the probability of winning as compared to losing. So odds gives you this um, uh, logistic regression problem. And the loss function in ORPO is basically you have a SFT loss, as you discussed, like the let's think step by step. So there you can learn about, the model can learn about SFT, like having actual tokens at the start of the sequence. And you also have that ORPO loss, that the logistic regression loss that I discussed just now. So, and there is a hyperparameter lambda. If the lambda is small, then you are primarily doing SFT. And if the lambda is midway, so you are amplifying the winning response, and you are reducing the probability of the rejected response. And chosen increases because of this SFT, because you will be doing SFT on the winning response, keep in mind. And the rejected responses needs to the likelihood needs to reduce because you have LOR. It is covered in the ORPO loss. And if your alignment is like hyperparameter is 1, so you have basically amplified this thing by a lot. Your alignment will dominate, and both chosen and rejected will decrease, and the margin will for the orpo loss will orpo loss for the rejected response will decrease even more. So there the idea is SFT will learn about the next tokens in your um, winning response, and your orpo loss will take care of reducing increasing that margin between winning and losing. Another important question here is why log odds instead of just odds? One is with the instability thing that I said earlier. Suppose like if you just took probability instead of log of this odds. So suppose like probability of winning is 0.9 and the probability of losing is 10 to the power minus 6. So it can overflow by a lot if you just took probability instead of log of the odds. So uh, probabilities is not very helpful, like it can cause a lot of instabilities because of this ratio that I showed you. Hence odds uh, odds kind of normalizes a probability, and the log of the odds is also very helpful in like stabilizing the training curve. And also another important thing is when you take raw difference in probability, this is for winning and this is for losing. So if the probability between 0.9 and for a token is 0.9 and for another token is 0.8 for losing, and also like if a probability of token is 0.2 and losing is 0.1, if you take the difference in these probabilities, it's just 0.1, same for both of them. But these two things tell a very different story. It means that the losing response is very close to probability for the winning response. So you need to reduce this probability by a lot so that you do not produce these losing responses. So, but if you take the log of this, as the sum is same, if you take the log of this, then you will get very different value. And you will care about this high probability tokens where the winning and losing is very close and they are really high in probability, and this will kind of different um, behave differently. So that's why we take log, so that if the winning and losing response probabilities or log probs are very close, so we need to do lot of alignment because the losing response is very likely in your policy, so you need to reduce it, reduce the chances of losing response by a lot. Okay, now let's start the last kind of preference optimization that we are going to talk about is Kahneman-Tversky optimization. So the need for this optimization comes from some of the problems that we had with preference data. One is collecting preference data is really hard. Like it's a special annotation process, um, and here a user has to see two responses, and based on different uh, rubrics has to say, okay, this response is better than this response based on this rubric. So it's kind of like really hard, and you cannot expect your customers to do this for you. But customers can actually do uh, thumbs up and thumbs down, or they can give a feedback of from 1 to 5 how good they felt about a response, or maybe something like was it really bad, or was it bad, or was it good, or was it really good. So customers can give a sense of this, and this is a great way to scale up your labeling. If you can have, instead of preferences, thumbs up and thumbs down as a way of feedback. And also preferences, like you have to pre-decide the rubrics. Like a response can be helpful but harmful, and another response can be less helpful but not at all harmful. So what kind of things are you optimizing for here? um, so this different dimensions of alignment is kind of hard to do. So let's have a way where we can label one response either positive or negative and try to learn from that preference, and KTO kind of helps with that. Before jumping into KTO, we have to discuss about prospect theory. In prospect theory, suppose this is your baseline level of emotions, and if something good happens, you say, oh, from your baseline, then you say, oh, I'm so happy about this. But if something even much better thing happens as compared to baseline, you say, okay, I'm happy. And if after that something better happens, then you just like your happiness saturates, and you say, oh yeah, whatever. But sadness and negative outcomes have a different kind of relation. So suppose this is your baseline level of emotions, and something a little bad happens with you. You say, or you start to feel the sadness. I'm sad. A little bit more bad, you say, I'm so sad. And a little bit more bad, it's I'm so depressed. So you see that range of things that are happening in happiness is quite a it's quite a high difference. But in sadness, humans tend to be with increasing loss, they become become sadder, and like the emotions that they feel from sadness is really high, and it's uneven in these two sides. So taking knowledge from this, and we can like see how we can help with preference data. And if I just have to go one level deeper in prospect theory, so your value function is established like this. If you are better than your baseline, so z naught is your baseline, and if your value that you got is more than z naught, so you have a value function that is kind of, it saturates after some point of time. So if you see like the alpha, like here, this is your baseline, and with alpha, like you are kind of like saturating really fast. If your alpha is low, which is in power here, so you're saturating really fast. So anything good that happens with you, you you don't feel a lot of emotions. But if you increase the alpha, so you definitely like start to feel more and more um, in your positive outcomes. And so this alpha kind of controls the linear utility. If your alpha is 1, so you have like linear utility in positive outcome, and if your alpha is less than 1, then you saturate really quickly, and if alpha is greater than 1, then you are like increasingly sensitive. So here if you see the yellow line which has low alpha, even in the negative outcomes, it saturates really fast. And as you increase the alpha, like your sensitivity increases, and you feel like more from your negative outcomes, or you feel more negative value from your negative outcomes. And so alpha is a way to control this sensitivity of your prospect theory. So taking ideas from this, So how is this helpful? Suppose imagine in a chatbot, like there is a response from the model, and you feel that okay, it's good, and you get another response which is little bit better. You don't feel a lot of, like, you're already satisfied with the earlier response which was good enough, so you don't feel a lot of value utility in having a second response. But imagine if it was the other way around, where you got a response and you had uh, a bad response and a response even worse than that. Your utility, like, oh damn, this is so bad, like your utility would be like that you are going to get is going to be so much, like your negative utility, that you are going to be super pissed about it if you get a response worse than the bad response that you got before. So uh, in preference data we need a way, if it is, if the model is producing better and better outcomes, we don't want our model to change too much because we are not getting a lot of utility from it. But if a model is doing worse and worse, we want to penalize our model really fast. We don't want it to go that much worse. So that's how the prospect theory lines up with KTO. So this is the loss function for KTO. And as I said, like in machine learning, you reduce the loss. So if you want to reduce the loss, so this lambda y is, so you basically have two hyperparameters here. One is lambda d, which is for desirable response or the winning response that you are talking about till now, and lambda undesirable, which is the losing response. So if you have these two hyperparameters, so this is combined here, lambda y, and you have this value function. So to reduce the loss, you need to increase the value function. And to increase, if you come back to here, your value function is basically um, given by this, if it is a desirable outcome or if the response is better than the baseline. And the baseline here is is the reference policy, or how close are you to the reference policy, how close is your policy to the reference policy. This is your baseline, and it kind of makes sense because you always have the reference model to refer to. And now, as I said here, we want to reduce the loss, increase the value function. Here, to increase the value function for desirable output, you need to increase this reward. And this reward is basically the log. This is the DPO log that that you have seen earlier. And you need to increase the reward under the constraints of KL. So this kind of makes sense, like you increase the reward based on and but you do not stray away too much from your reference model. But if the value is undesirable, you can see like the it's kind of flipped, and here z naught is without a negative sign and the reward is with a negative sign. So to increase the value, you need to reduce this r theta x comma y, which makes sense. You need to reduce the log probs of your undesirable outputs. And also we need to increase the KL divergence. So we want like our reference model suppose produces bad response for a like has really um, high log prof of the bad response. We want to make it we want to increase the KL divergence and make the desirable response undesirable response even less likely than the reference model. So which kind of makes sense, like if you have the reference model and you want your policy to train such a way that even if reference model has really high log prob or likelihood of the undesirable response, you have really bad you have really low likelihood for that undesirable response. So this kind of like really helps with uh, like having the undesirable and desirable response. And now you can see like these are two different objectives that you're optimizing for. And suppose like you have a preference data, the winning response can come here and the losing response can come here. So now you have a way to separate out the winning and the losing response and optimize them separately. So this is about KTO. Thank you.